let's start our presentation by young researchers. So the first young researcher is María Chara from the Instituto de Matemática Aplicada del Litoral in Argentina, and she will speak on subtowers of function fields.
Thank you. First of all, I want to thank Carolina and all the organizing committee for having these sessions, presentations from young researchers, because this is really good for us. And so thank you very much. As she says, I'm going to talk about subtowers of function fields. And you must know that this is a work in progress with Horacio Navarro from Universidad de Cali in Colombia and Ricardo Toledano from Universidad Nacional del Litoral in Argentina. So I'm going to talk about function fields, so I will recall quickly what a function field is. This is just a finite extension of the rational function field, and the rational function field is obtained by adjoining a transcendental element to the finite field FQ. Since I'm going to talk about towers, you must know what a tower is, and this is a sequence of function fields over the same finite field FQ, such that each function field is strictly contained in the next one. All the extensions are finite and separable, and FQ is the full field of constant of every Fi. And we also need a technical condition, which is that the sequences of genus tends to infinity as I tend to infinity. The motivation of why do we are interested in studying this type of towers is on codes that Luciani already talked about this. With these towers, especially with a special class of towers which are recursive towers, Arnaldo Garcia and Henning Stichenhoff could prove that there exists a sequence of codes that improve the already known bound of Gilbert and Barjamot with this code. So what a recursive sequence is? You need that every function field in the sequence is given by a polynomial like this. So what you do is the first function field is just the rational function field. And then you have the next one is just the previous one, and x1, where h of x0, x1 equals 0. And then to construct the next one, you do it exactly the same. So if you do this, you know exactly how these fields behave, or at least you know more about this. But not every polynomial will give you a tower, so a suitable choice of this polynomial must be made. And we will work with what we call AV recursive towers, and this is when this polynomial has a special form that is separable in the sense that you can have these two functions, A and B, and then what you have here is that this is A of x1 equals B x0. Well, in order to have this improvement for the bounds of, for the relative, for the parameters of the code, you must know the asymptotic behavior of the tower, and to study asymptotic behavior, we study what is the limit of the tower, which is this limit where Fi is the number of rational places of every field in the sequence, and G is the genus. This limit always exists, and if it is bigger than 0, we say that the tower is asymptotically good, and if it is 0, then we say that the tower is asymptotically bad. In order to have these codes that Luciani talked, we need asymptotically good towers. So we are interested in finding a way to have asymptotically good towers. But this is not always easy, so what we did is to study not the tower itself, but a subtower. What is a subtower? Basically, what we do is we construct another tower such that it's inside this one. For example, if I take, I don't know, some polynomial f of x0, then this is inside f0, and then I have a tower here. And this could be inside this one or this other, and then we go on like this, and then we have a subtower of the original tower. And why do we care about subtower? Well, because it is well known that the limit of the subtower is bigger than or equal than the limit of the tower. So if the original tower is asymptotically good, this is bigger than 0, and then the limit of the subtower is also good. Or if the limit of the subtower is 0, this is that the subtower is asymptotically bad, then the original tower is also asymptotically bad. Then sometimes, if we cannot work with the original tower, we could find a subtower or a supertower and try to find, to say something about this new tower. So what we did is to give a computationally adequate method to construct subtowers of towers that are AB recursive towers. How do we do that? We take any AB recursive tower, and we try to find irreducible functions f, a tilde, b tilde, such that this equality holds. So you say, that equality is a bit odd, but, well, it happened that many towers have these functions existing. And then if you can find f, a tilde, and b tilde like this, then you have a subtower because you put set I, f, a, xi, and then the first field in your subtower will be fq sit 0, and all the others are given in this way, where now we have that this equality holds. So this new subsequence is recursively defined by a tilde, b tilde. And also in this case, we have that every field is contained in the one with the same index. But with this method, you don't know if E is a tower. You just know that it's a subsequence, and you have to prove now if this is or not a tower. But the first thing that we did was to prove that this was actually a proper subsequence of the original one, because we don't want to have another representation of the same fields. And this was done in this theorem. If we have these conditions that are really easy to check, then we have that the recursive sequence is strict. Yeah, I mean, this subsequence is proper as a subtower of the tower F. And as I say, these are conditions that are proved only on the degree of the rational functions defining the extension, so are really easy to check. So as examples of this method, the first example that I want to show is taking this tower that was studied by Garcia, Stissenov, and Rack in, not this year, 2003. No. 2003, they proved that this tower is asymptotically good. But here, if we take, well, A and B are this one, which are the rational function defining the tower. Now here, if we have F equal to this, A tilde, B tilde, then this composition holds, and we have this subtower, subtower E given by this equation. And this was the first example that appears for us, and it was already known because Maharaf and Mustang already found these subtowers, but they use a method due to Elkis. And this is a really simple proof that this is a subtower of the previous one. But this was an already known example. Another interesting example is when we took this other tower. This tower was already known by Garcia and Stixon and Bragg in the same article, but they say, well, we have all of these towers, and they, surely they know, but they didn't say that this was also a subtower of the two previous ones. If we take this A tilde, B tilde, and this F, T plus 1, then we found that this one is a subtower of the tower in the previous example of this one. And also, of course, is also a subtower of the previous one. So these methods also allowed us to compare different examples to see if they have any relationships or not. Another example of what we did is to take this equation of Artin-Schreier type, studied by van der Gier and van der Vlag, and we also found subtower of this tower, taking this this one, these functions A tilde and B tilde, and this T, and these compositions also hold. And we have this, the subtower given by this equation. At the first sight, if you see, this seems to be a degree 3 equation, but this is actually reducible. So this is again an extension of degree 2, and for this equation, our theorem also holds. This is a proper subsequent, and this subtower was studied by Caro and Garcia in a more general way, but they found that this was a subtower of the previous one. But they said, well, we don't know what happened with this one, which is really similar. So what we did now is to try to find subtowers or supertowers of this one, and we found that if we take this function to be A, this to be B, this A tilde, B tilde, and then F is T plus 1, then this tower is a subtower of this one. And this tower was the only one left in another work of Garcia-Stixenov, where they classify all the Artin-Schreier towers in characteristics 2, and they say which of them are good and which of them are bad. And then they say, well, and we have this one that we don't know yet if it is asymptotically good or asymptotically bad. And we start studying this one, and it seems to be asymptotically good, but we couldn't prove it. And then we start looking at this one, and then we could prove that this tower is asymptotically good if we take even power of 2. Actually, this one is asymptotically good for even power, and it's asymptotically bad for odd powers. And so this one is also an asymptotically good tower of function fields using the known inequality for the limits. So this is the original example that we could get using this method. And well, we think that we are going to continue working with this. So well, that's all. Thank you.